And welcome back, Professor Almeida, jpalmeida.com. Welcome to another lecture in my series on critical thinking. And today we're going to look at inductive arguments. We're going to evaluate inductive arguments, and we're also going to look at probabilistic and statistical fallacies. Now, this lecture coincides with Chapter 3 of the OER textbook, Intro to Logic and Critical Thinking. So if you are in my COSA 2 class, Critical Thinking Using Computers, please have a look at Chapter 3 going into this presentation. Now, it's also important to note that there is quite a bit going on in this chapter. I won't get into everything. If you need to, you can pause the video, open the PDF, get right into Chapter 3, find what you need, and then I'll be waiting right here. So if you need to, again, feel free to pause this video. If you value what I'm doing, if you're getting any value out of this, feel free to hit that like button, hit that subscribe button, and let's get right into it. So by the end of this talk, and after reading Chapter 3, you should know how to deem good generalizations, quote-unquote good, be able to identify and describe the 7 explanatory virtues as discussed in Chapter 3, be able to evaluate analogical arguments, identify causal generalizations, be able to use probability to evaluate inductive arguments, and finally, looking at fallacies, identify conjunction, base rate, small numbers, regression of the mean, and Gamler's fallacies. And I want to step back and review what inductive arguments are. And if you recall from Chapter 1, inductive arguments try to show that their conclusions are plausible or probable given their premises. Take, for example, so far in every class, Professor Almeida has worn a sweater. Well, not wearing a sweater here, but again, for the sake of argument. So far in every class, Professor Almeida has worn a sweater. Therefore, Professor Almeida will wear a sweater next time in class. Now, this is an inductive argument because there is a possibility that the conclusion could also be false. And it's important to note that it's unlikely that the conclusions won't follow from their premises. And I want to explore this more by looking at this next example here. 80% of voters say they will vote for Joe Politician. Therefore, Joe Politician will probably win the election. Here's my question to you. Can the conclusion be false? Now, this is an inductive argument because even if the premise is true, the conclusion could still be false. For example, Joe Politician's opponent could intimidate those voters who intend to vote for Joe Politician so that very few of them will actually vote. Now, if you want to be a little more grim, Joe Politician's opponent could systematically kill off all those voters, and then Joe Politician won't win the election. So again, it's an inductive argument because the conclusion could still be false. And in assessing whether or not a statistical generalization is true, we need to consider two conditions. Number one, you need to have an adequate sample size, that is a portion of a population. And before I continue here, I want to make a note that the reading does a pretty good job with the key terms. I won't get into much about key terms, but again, if you need to, you can pause this video, you can go to the reading, and then come right back here when you are ready. The second condition is a non-biased sample, and you want to be careful in committing the fallacy of hasty generalization. And that happens when one infers a statistical generalization about a population from too few instances of that population. Take, for example, you infer that it snows every day in Flagstaff because it snowed on the one day you went there. That is committing the fallacy of hasty generalization. And you're going to find that this fallacy works especially well when agendas are involved, when fear or other practical interests are also involved. You'll see this a lot in arguments. Let's also look at bias. Now, again, the book goes through a couple of examples in polls. So let's say that Joe Politician's running for elected office, strongly supports gun rights, and is the candidate of choice of the NRA. And let's say that an organization runs a poll to determine how Joe Politician is faring against the opponent who is actively anti-gun rights. But let's say that the organization administers the poll by polling subscribers to Field and Stream magazine, which, if you know anything about that magazine, the subscribers would tend to own guns and support gun rights. Well, by polling those subscribers, the organization has bias, right? There's bias in the polling here. Let's also look at how the question is worded in this example. Which do you favor? A, preserving a person's constitutional right to bear arms, or B, leaving honest people defenseless against armed criminals. Now, looking at how this is worded, option B here looks really bad, right? Who would want to leave honest people defenseless against armed criminals? So even if you weren't for gun rights, you might be more inclined to go with the first option here. So if the question is biased, your statistical generalization will be biased as well. And it's important to note that when it comes to going through the material in this book, it always takes practice. You can't just read through the chapter or watch this video and come away as an expert on this. You have to keep practicing. When it comes to critical thinking, you always have to practice those skills. Let's take another example here. Greg from Huntington Beach drives a 4x4 pickup, so most people from Huntington Beach drive 4x4 pickups. What's wrong with this generalization? Again, remember what we just talked about with the fallacy of hasty generalization and what we just talked about with sampling. Okay, so again, make sure you go through the exercises in the reading. Make sure that you understand why the answers are what they are. You do have the answers in the back of the book. And let's get into inference to the best explanation by looking at this scenario. Let's say you get to your car and you find a broken window and the phone that you left in your car is missing. Okay, so you get to your car, the window's broken out, your phone is missing. The immediate inference you would probably make is that someone broke the window of your car and stole your phone. Well, what makes this a reasonable inference? What makes it reasonable is that this explanation explains all of the relevant facts, right? Here we have a broken window and a missing phone, and it does so better than any other competing explanation. And I have a couple of them here. Did a stray baseball break your window and someone just happened to take your phone? Well, what if you weren't parked next to a baseball diamond or a field? What if a dog just happened to jump into your already broken window and ate your phone? Well, that means someone would have had to have broken the window, but who breaks a window and doesn't take the phone, right? It doesn't seem like it's the best explanation. So what's the best explanation? Let's break this down into these 4 items here. Let's start with the observation. Okay, the observation here. Your car window's broken and your phone is gone, right? The phone that you left in your car, it's gone. So you form a hypothesis, right? You form a guess. A thief broke your car window and stole your phone. And now let's compare the other inferences. Let's look at the other explanations. Stray baseball breaking your window and someone just happens to see your phone and just, you know, reach into that broken window. They get into your car and they take your phone. Did a dog jump into your already broken window? So in looking at this, no other hypothesis provides as reasonable an explanation. Your conclusion, therefore, a thief broke your car window and stole your phone. Now, in going through the Chapter 3 reading, you will come across the 7 explanatory virtues. These are the 7 virtues here: Explanatoriness, depth, power, falsifiability, say that 3 times fast, modesty, simplicity, and conservativeness. Again, if you need to, feel free to pause this video and come back when you are ready. So let's start with the first explanatory virtue, explanatoriness. According to the reading, explanations must explain all of the observed facts. Suppose a friend came to you and told you that your best friend broke into your car. Well, what if your best friend, okay, maybe you really know your best friend. What if your best friend could easily buy the phone you had? Right? Your best friend never stole a thing. So here, the explanation actually raises more questions and lacks depth. And depth is actually the next explanatory virtue here. With depth, explanations should not raise more questions than they answer. So your best friend probably wouldn't break into your car. Now let's look at power. A good example would be the stray baseball. That's, you know, the stray baseball scenario is supposed to explain the breaking of the car window. Well, what if there's no baseball field nearby? Maybe you parked on the street or you're in your apartment complex. The next question, well, who plays baseball on your street or in your complex? Now, on the other hand, maybe here's another explanation. Many windows broken on the street or in your complex can be explained by thieves. So the second explanation, that many windows broken on the street or in your complex are explained by thieves, that's a more powerful explanation. Does that make sense? Falsifiability. It must be possible for there to be evidence that would show that the explanation is not correct. With modesty, explanations should not claim any more than is needed to explain observed facts. The hypothesis should not be more specific than it needs to be. So let's take, for example, your friend comes up to you and says, "Hey, I think I have a hypothesis or a guess as to why your car got broken into. It was a green-haired man with a Tasmanian devil tattoo." How does green hair and a tat explain why your car windows are broken? That's more details than you needed. Okay, so that's what the modesty virtue is. Simplicity. You've probably heard of Occam's razor. If not, again, you can go Google it. And this is what it basically is. The simplest explanation is the better explanation. Let's suppose there were two other cars parked next to yours and they also have broken windows. So let's look at one of two explanations. 3 separate, unrelated thieves, or perhaps one thief or group that broke into all 3 cars. Again, the simplest explanation is the better explanation. So we're going to lean towards the latter here. One thief or group that broke into all 3 cars. Finally, conservativeness. Explanations that force us to give up fewer well-established beliefs are better than explanations that force us to give up more. Take, for example, Bigfoot. Does Bigfoot really exist, or is it just someone dressed in a gorilla suit? Well, one explanation requires the existence of Bigfoot, contrary to well-established beliefs that Bigfoot is folklore. Now, on the other hand, if you want to explain that it's someone dressed in a gorilla suit, well, that doesn't require the existence of Bigfoot in the first place. Does this make sense? Let's move on to analogical arguments. Again, if you need to, feel free to pause this video and I'll be waiting right here, or you can just come back at any time. Remember where you left off. And as always, if you're getting any value, hit that like button, hit that subscribe button. So let's look at analogical arguments. Joe has always owned Toyotas in the past and they've always been reliable. Joe argues that the new car he purchased will be reliable because it's a Toyota. Well, is this a strong or a weak inductive argument? Well, we need to figure out how many Toyotas Joe has owned. If Joe owned only one Toyota, well, remember what we just talked about, committing fallacies of hasty generalizations, right? So if Joe only owned one Toyota, well, that's going to be a pretty weak argument. But on the other hand, if Joe owned 10 Toyotas before this new car, then it's a stronger inductive argument. Now, what if the new Toyota has significant changes in its suppliers? Maybe it's a different drivetrain from previous Toyotas, right? So that could also affect the argument, right? It can make the argument weaker. And the takeaway from this is that arguments from analogies are strong when characteristics of what's being compared are similar in relevant respects to the characteristic in the conclusion and no relevant lack of analogies. Let's look at causal generalizations, and we're going to use another example here. Let's say you come across your dog and you're asking the question, okay, why is the dog sick? Is the dog sick because the dog ate human food? Was it the shampoo bath, the flea treatment, the dog's not regularly eating? Okay, well, let's keep a log, and here's the log that I have kept for 6 days. Okay, so we're observing your dog getting sick. Here's the log. On day 1, the dog didn't eat human food, had the shampoo bath followed by the flea treatment. We saw the dog was eating regularly, and yet the dog got sick. Day 2, ate the human food, didn't have the shampoo bath, but still got the flea treatment. We saw the dog was eating regularly, but the dog didn't get sick. Day 3, human food, yes. Shampoo bath, but this time no flea treatment. Was eating regularly, still didn't get sick. Day 4, ate the human food, had a shampoo bath followed by the flea treatment, but we also saw the dog wasn't eating regularly and got sick. Day 5, again, ate human food, had the shampoo bath but no flea treatment. We saw the dog was eating regularly, didn't get sick. And then finally on day 6, human food, no bath but got the flea treatment, was eating regularly, didn't get sick. Okay, so take a moment, look at this table. Again, if you need to pause this video, please feel free to do so. And we have 2 tests here. One's called the necessary condition test. The other is the sufficient condition test. When it comes to the necessary condition test, any absent feature, okay, so these are all features here, right? These are features. When the target is present, okay, that's sick. Think of these as variables, right? When the target is present, is eliminated as a possible necessary condition of the target. So we see from looking at this that human food and eating regularly can't be necessary conditions. Now, we also notice that every time the dog is sick, the dog had a shampoo bath followed by flea treatment. Okay, sufficient condition test. Any candidate feature when the target feature is absent is eliminated as a possible sufficient condition. But in looking at this, no one candidate feature is sufficient condition. However, it's still possible that certain features are jointly sufficient. And we do notice that on days 1 and 4, the dog got sick only after the shampoo bath followed by the flea treatment. So we can say that the likely cause of the dog getting sick is from the shampoo bath followed by the flea treatment. And again, I hope this makes sense. A similar example is in the reading, and you'll see the tables drawn up with the variables. Now, you want to be aware of the false cause or post hoc fallacy. We can't say that just because X is correlated with Y, that X caused Y. And this fallacy occurs when someone assumes that X and Y are correlated and must be in a causal relationship. In other words, saying that X causes Y. Let's switch gears and talk about probability. So probability looks at how likely that something is or will be true given a body of evidence. And we have a couple of different examples we can use. And let's consider this scenario. Let's say that I have a deck of cards, right? Standard 52 card deck. I want to know what the probability is of me drawing an ace. Okay, so when you look at a standard deck of 52 cards, you have 4 aces, right? There's 4 different suits. You have the clubs, the diamonds, the hearts, and the spades. And within each suit, you know, you have your numbered cards. You have jack, queen, king, ace, right? So there's 4 aces. So with that said, the probability of drawing an ace, again, there's 52 cards, there's 4 aces, so it's 4 in 52, or a 7.7% chance. That's the probability of me drawing an ace. Okay? Moving right along. Let's say I want to know the probability of me drawing an ace, and then after returning it to the deck, drawing another ace. This is looking at the probability of a joint occurrence or conjunctions. And to determine the probability of a joint occurrence, you take the first probability, you multiply it by the second. Okay, so as we established here, the probability of drawing any one ace is 4 in 52. Remember, there's 4 aces, there's 52 cards in a deck. And in this example here, let's say that I draw the ace, I put the ace back in the deck, I reshuffle it, and I want to know the probability that I'm going to draw another ace. So it's going to be 0.077, right? 0.077 times 0.077, and that basically is a 0.59% chance. That's a less than 1% chance of me drawing an ace, putting it back, and then drawing another ace. Okay, that's a less than 1% chance. Now, what's the probability of me drawing a heart or a diamond? Okay, so this is the probability of a disjunction. And to find the probability of a disjunction, you simply add the 2 probabilities. Okay, so remember, there are 4 suits in a deck of 52 cards, which means that there are 13 cards to a suit. Okay, so the chance of me drawing any one suit is 1/4, right? 13 and 52. So that's a 25% chance. So here we just add up the two probabilities for hearts and diamonds. So 25% chance of drawing a heart, 25% chance of drawing a diamond. That's 50%. Now, any poker players out there? If you're a poker player, you want to know what the chance is of drawing a flush. This one's for you right here. So a flush, it refers to 5 cards in the same suit. Now, you have to think about what the probability is going to be. So your first part here, your first card, right? Your first card of drawing something out of a certain suit, whether it's a club, a spade, a diamond, or a heart, that's 25%, right? 13 and 52. But you're still holding on to that card, which means that there are 51 cards left in the deck. And because you've already drawn one card out of the suit, that leaves 12 more cards in that suit. So for your second card, the probability would then be 12 in 51, right? You draw that second card. Now you have 50 cards in the deck, and 11 of those remain in that from that suit. So for the third card, it's 11 and 50. Your fourth card would then be 10 and 49, and finally your fifth card would be 9 and 48. So you multiply each of those probabilities for each card, right? So 13 and 52 times 12 and 51 times 11 and 50 times 10 and 49 times 9 and 48. And that will get you 33 in 66,640, or a 0.05% chance of getting a flush. And as you can see, getting a flush in poker is a very rare hand. Don't even get me started on a straight flush or even a royal flush for that matter. Okay, so I hope, again, this makes some sense. If you need to, please practice with those exercises in the reading. And let's ask this question. What about a flush in any suit? And what we're going to do is we're going to add the probability for each suit. Okay, we've already established here 0.05% or 0.0005, and you're going to add that for each suit, which again, the probability of getting a flush in any suit is 0.2%. Now, you have to be careful with fallacies here. Okay, we're going to get a little bit into fallacies, and we're going to start with the conjunction fallacy. Conjunctions can never be more probable than either of its conjuncts. Okay, so if we draw cards from a shuffled deck, what's more probable? Drawing a club or drawing an 8 of clubs? So let's calculate out those probabilities here. So the probability of drawing a club, it's 13 and 52, right? So that's 0.25. Drawing an 8, okay, drawing an 8, there are 4 8s in a standard deck, so that probability is 0.077. Now, if we're going to draw an 8 of clubs, we're going to multiply those two probabilities. So we're going to multiply the probability of the club, 0.25, times the probability of getting an 8, 0.077. So your chance is 0.019. Base rate fallacies. Let's say there's a machine that can detect terrorist behavior with 90% accuracy, right? The government came out and said, hey, we have a machine that can detect terrorist behavior. Minority Report style, if you've ever seen that movie, right? Let's say it's 90% accuracy. There's a terrorist in the building. Security seals all the exits and rounds up all 3,000 people in the building. Okay, so if you want to look at this, this is on page 179. So, all 3,000 people go through that machine. The first 30 people pass through the machine, but the next person sets it off. What are the chances then that the person who set off the machine really is a terrorist? Do you think it's 90%, 10%, or 0.3%? Take a moment to think about it. I'll be right here waiting. If you said 90%, you just committed the fallacy. Okay? So, again, given this scenario, the probability of any one of the 3,000 being a terrorist, that's 1 in 3,000. 90% accuracy means that 10% will be misidentified. Okay, 10% of 3,000, that's 300 people. Let's assume that the machine does not misidentify the terrorist. That's 301 people. So the probability of any one of the 301 being a terrorist would then be 1 in 301, or 0.3%. Small numbers fallacies. Samples which are too small will tend not to be representative of the population. Small samples tend to the extremes, and those can either be overrepresented or underrepresented. And when we commit this fallacy, we tend to look for causal explanations and we ignore the sampling. Regression to the mean fallacies. Let's talk snake oil. Let's say that I take a product to help me recover from a cold, and a few days later I'm better. So, I get a cold, somebody convinces me, hey, you should take this product, it'll make you get better. And a couple days later I'm better. So, was it the medicine, or did I regress to the mean? So what does it mean to regress to the mean? Regressing to the mean simply means you go back to normal. So was it really the medicine, or was it because that when I was sick I was outside of what normal health would be? Okay, so we can't say it's the medicine. Let's also look at hot streaks in sports, right? Let's say Steph Curry shoots 15 three-pointers in the last 10 games, but then suddenly scores less three-pointers, and the ESPN pundits start to speculate, right? They're all on TV. They're saying, oh, Steph Curry, it got into his head. Well, did fame get into his head, or did he just start playing like everyone else? So, what can we do here? Maybe we can get that snake oil salesperson to agree to a study with experimental and controlled groups to see if it really is the medicine, right? Let's see those people who get sick. Was it because of the medicine, or maybe they didn't take the medicine and they got better anyway? Finally, we have the gambler's fallacy. With the gambler's fallacy, one thinks that independent random events can be influenced by each other. Take, for example, let's say you flip 4 heads in a row, your friend flips 4 tails in a row. Who should you bet flips the head? And again, we're talking about fair coins here. So if you bet on your friend because your friend flipped 4 tails in a row, and you're thinking, okay, all right, it's already been 4 tails, the next time's got to be a head, right? That's the gambler's fallacy, because you have to keep in mind when it comes to probability, with a fair coin, each flip, it can go either way, right? You have a 50% chance of it being heads and 50% chance of it being tails. So anyway, that's the end of this lecture, and in closing, all I have to say is practice. Practice. Don't just close out of this video, just go, or just read through the chapter and think you know everything, okay? Always practice. Again, make sure you understand why the answers are what they are, and if you got any value out of this video, feel free to hit that like button, hit that subscribe button. Great chatting with you as always, and we'll see you in the next video. Have a good one.